Добар ден. Се надевам дека сме сите сити и можеме да продолжиме со сесијата. Наредното предавање е од повиканиот предавач, професорот Алпер Илки, заедно со група на автори Чаглар Гоксу, Билал Сари, Хасан Хусеин Айдоглу, Гем Демир. Се надевам дека точно ги прочитав имињата. Трудот е 2023, Kahramanmaraş, Earthquakes and Lessons Learned Towards Building Resilient Cities with a Focus on Istanbul. Пред да продолжиме со предавањето на професорот Алпер Илки, ќе прочитам негово кратко CV. Dr. Alper Ilki is a professor of structural engineering at Istanbul Technical University. His research interests include the structural behavior of reinforced concrete and masonry structures. Other main fields of his research interests are large-scale structural testing and structural seismic retrofitting, particularly through innovative techniques and materials. He is the editor of Turkish Journal of Civil Engineering, associate editor or editorial board member of Aster Journal of Structural Engineering, Aster Journal of Composites for Construction, Arabian Journal for Science and Engineering, and Bulletin of New Zealand Society and Earthquake Engineering. He co-edited 3 international books published by Springer, titled Seismic Risk in Assessment and Modeling of Earthquake Loss. Dr. Ilki is an elected member of the IIFC Council, head of Turkish delegation to FIP, chairman of the executive committee of Turkish Earthquake Foundation, and a member of the board of Turkish Catastrophe Insurance Pool. He chaired and co-chaired the organization committees of Smart Modeling, Assessment and Rehabilitation of Civil Structures, International Conference Series, and the 10th International Conference on FRP, Composites in Civil Engineering, CICE 2020 and 2021, the official conference of IIFC, as well as the FIP Symposium in 2023, among many others. So, Professor Ilki, the floor is yours.
Thank you, Chairs. It's my great pleasure to be together with all of you and to make this presentation. Many thanks to the organizer for inviting me to this important event. The chairperson read the title, so I'm passing this slide. This is the content of the study. I'll briefly summarize the consequences of the earthquake and then what we do in Istanbul to make the priority of the buildings in terms of seismic risk. And I will a little bit talk on seismic structural retrofitting. Just to give you an idea, in Turkey we have quite good seismic design codes since 1940. Right 1 year after 1939 Erzincan earthquake. And then we have always revised the code. And the seismic code in Turkey is not somehow below US codes or European code. It's quite high standard code with up-to-date information in it. This graph shows the revisions of the codes as well as the earthquakes that we had experienced on the bottom line. And the bars show the number of buildings constructed in different time periods in Turkey. We always consider that year 2000 is a kind of important milestone in Turkey because of the 1999 earthquakes we had. They were catastrophic and many persons get a lot of lectures from that. Still we have many buildings which were built before 2000. So this at the first hand seemed to be the most high-risk building stock. If you look at the earthquakes that we had in February, we had several earthquakes and about 40,000 aftershocks to different magnitudes. But the first one was 7.7, a huge earthquake which fractured about 300 kilometers surface. And the others are seen here. I'm not going to go into the details, but the death toll was more than 50,000. and the injuries are more than 100,000, with a financial cost which is estimated to be over 100 billion US dollars. These are some appearance of the surface ruptures, which is, as I mentioned, as long as 300 kilometers and 130 kilometers in the first two earthquakes. And there are lateral displacements of more than 6 meters. Even some persons report the lateral displacement of more than 10 meters in some locations. This graph is very nicely showing what we had in Turkey in February. Last line shows the 3 earthquake ground motion records, only February 2023 earthquakes. The first 2 lines belong to all other big earthquakes that we had in recent 30 years, including Kocaeli earthquake, 1999, and 1992 Erzincan earthquake. So if you look at them and if you compare them, if the last line is a kind of earthquake series, the others are like baby earthquakes or vice versa. I mean, these are totally different in scale, magnitude, duration, and so on. The accelerations were in the order of 2G, ground acceleration in the both horizontal directions, as well as vertical accelerations over 1G. The bridges have just jumped, and the supports of the bridges have fallen down in some locations. Many people say that this is the largest earthquake that happened on the land, not on the ocean. So directly, like about 14 million people were affected from the earthquake. Those cities are now like, many of them like ghost cities. There's nobody there other than working people demolishing the buildings and so on. Here the calculated spectral accelerations are compared with design accelerations, but these design accelerations are not for ordinary buildings. These are for important buildings like hospital, schools, etc. And as you see, for a wide range of natural periods, these design accelerations were remarkably exceeded. And you can imagine that these exceedance is much more for design of ordinary structures. Then that's normal that those buildings would be damaged in the area. What is not normal is the collapses of the buildings. The damages, heavy damages would be okay if those buildings were not collapsed and did not cause casualties. If you look at the damages of the buildings in the area, this is like in 11 provinces, and maybe larger than many European countries, only this region. The total amount of buildings examined is more than 2 million, and about little more than 1 million are reinforced concrete structures. The gray bars shows the damage distribution for overall building stock in the area, and the red bars show the damage distribution for reinforced concrete structures. If you look at last 3 columns, which are heavy damage and beyond, collapse, partial collapse, and so on, so it shows that about 12% of all buildings in the area experience heavy damage or worse. And for reinforced concrete, this is at around 8%. I should tell you that this is a little bit more pessimistic than actual damage, because often damage, I said, they're trained actually. I also give training to those guys online and on-site physical. But when they need to decide, they are quite anxious. They think that whatever, if an aftershock happens and if this building collapses, I have decided that there's moderate damage, but if it's collapsed, I'm in trouble, and so on. So they tend to give little heavier damages, which is too bad because now we have a very huge stock of heavily damaged buildings which should be demolished. And all this now, people are for months demolishing those buildings. Still, we have a lot of buildings to be demolished. Where will those people live? How much time does it take to reconstruct those buildings? Is a great problem. And unfortunately, you can't do anything because at that time, about 10,000 people were on site making damage assessment. They just had a training of like few hours and then they are on site. So we have been thinking that year 2000 is a milestone because of many things. Most importantly, because of 1999 earthquakes. Because it makes a lot of consciousness, hopefully, for the people, for the administrators, for the engineers, workers, everybody. And also there are other things. In 1998, the code was revised, and we have been using the capacity design principles, all ductile details, everything was quite perfect. Reinforced concrete design code was also revised in 2000. The material use was much better. Ready-mix concrete everywhere, deformed bars everywhere. And also the inspection mechanism has been changed. Hopefully it would work much better with respect to previous one. Was it the case? If you look at the damages of the buildings with respect to their construction year, these are all buildings in the area. Either the blue ones, the blue bars show the buildings constructed before year 2000, and the orange ones shows the building constructed after 2000. If you have a general look, you see that yes, there is some improvement, obviously. Buildings constructed after 2000 behave remarkably better, but not sufficiently. As you see here, still about 8,000 buildings were collapsed, which were built after 2000. This is quite disappointing for us. Although situation has been improved, if you look at this table, collapsed buildings are about 1/3 with respect to older buildings, partial damage like that, heavy damage like that, but still we have many buildings heavily damaged or worse. And the main reason is insufficient ductility. We have never seen a building with sufficiently ductile constructed and collapsed. All the buildings in all cities, in this earthquake and previous earthquake in Turkey, the main reason of damage is not application of sufficient ductile details. So we have to do something for easier application of ductile design details on site for new buildings, and we have somehow to make the existing buildings more ductile to avoid such losses. A summary about the field observations. We had some, by the way, I want to take a lot to our Macedonian colleagues because they have offered a lot of help after the earthquake, and many other international groups also supported us. Material problems exist, particularly for old structures. The concrete quality is about the half of what it should have been. Half, like 10 megapascal everywhere, average. For the build, 10 megapascal compression strength for existing buildings all over Turkey. That's average, which means that there are a lot of buildings which were built with 8 megapascal, 6 megapascal concrete, if you call it concrete. For new buildings, it's a little better, but still we had some problem, not only in terms of compression strength of the concrete, but the workmanship, the placement, curing, etc. So still some problems there in terms of practice. Worse is the details in terms of ductile behavior. No hooks of 135 degrees steel, no cross ties. Engineers don't think that cross tie is something important. They think it's a detail. You could do it or not. So we just really think of changing the cross ties, but using other closed syrups, because we never can tell it to the engineers or the workers. There is no construction with 135-degree hooks and properly placed cross ties, which end up with such failures. Very good concrete, new building, this is just under construction during the earthquake, 12-story. Even it's not fully loaded, no finishings, no walls, no light loads, but it collapsed. And there are a lot of shear walls. It's not a matter of structural system, a good structural system, good concrete, deformed bars, and so on. But you see the shear boundary of the shear wall. There is no confinement. So obviously there is a strength is exceeded, there is crushing, and then bars are fractured on the tensile zone because of high rotation. And we had still some, although we are using capacity design principles for more than 25 years, still we have shear failures. We have strong beams and weak columns for the new buildings, ending up with such kind of consequences, which we never would like to have. Of course, there are other problems about connections, about diaphragms, about insufficient stiffness, which could bring us to this kind of damages. These buildings would collapse if the earthquake was going on 10 seconds more, probably, and many of them has been already collapsed. You see the residual drift is like more than 10%. Luckily, it is still standing. We had soil-related problems in certain regions near the lakes and so on, so a lot of liquefaction, which is good because people are not dead within these buildings. they can survive, but of course the buildings are not used afterwards. And non-structural system, one of the keynote lecturers mentioned about this. We don't pay attention to those. We overlook them. There are some unimportant details, but many buildings, I mean like hundreds of thousands of buildings, were just unusable after the earthquake, right, just because of the non-structural damages, including hospitals and schools, which should be used right after the earthquake. So we should do something. Actually, in 2018 code, we brought some new recommendations about the design of the infill walls, and we put stricter limits to displacement if the walls are tightly connected to the frames, but nobody applies. And finally, this is the consequence. I mean, in seismic countries like us, I don't think we need this kind of good, nice, beautiful details. I hope there is no architect here, because they are destroyed during the earthquake, and you cannot use such places where you need a lot, because you need some shelter for the people. It was -10 degrees. There's a large hospital, large school, just cannot be used because of damage of plasters, finishings, and so on, suspended ceilings. If you look at public buildings, they performed a bit well because they have more regular structural system, a bit better inspection, and they are generally lower rise structures. Except this hospital building in Iskenderun, which was built in 1968, and obviously it was a very wrong decision to use it. They have prepared some reports about it. It's not safe, and when you look at it, it's clear it's not safe. And a part of the building was collapsed with many doctors and patients dead in this building, unfortunately. Recently, in high seismic zones, the hospitals are built with base isolation system in Turkey. As far as I know, Turkey is the country which is using the most of the isolators in the world. They generally perform well with some problems, which have been made during the installation or after the installation. The free movement of these isolators has been prevented due to some details, architectural interventions, so they somewhere didn't work well or not fully. This caused some damages on non-structural systems, but overall, there was no big problem as far as I know. High-rise structures are not common in the region. This is the only one that I have examined in detail, like 42 stories and 37 stories, several blocks of them. This is in not a very heavily affected zone, but in these areas, just with some slight damages on the non-structural members, as well as some fine cracks on shear walls and columns, but can be used right after the earthquake, which doesn't necessarily mean that if this was in a very heavily affected zone, it would be the same or not, we don't know, of course. Tunnel form buildings, these are, I don't know, it's a common terminology in Macedonia as well. Tunnel form building is a building with all shear walls and flat slab. There's no column and there's no beam. Performed well. Architecturally not good, nobody likes it, but they didn't cause any casualty. So people were happy to be in such kind of buildings. The question was now, some of them were heavily damaged, as you see. And by the way, there are a lot of mistakes in these buildings as well. They are not constructed properly, but although there have been made many mistakes in their construction, they survived simply because there are a lot of shear walls, very strong lateral load resisting system. And the final decision was to repair and retrofit those buildings rather than demolishing them, which would be very costly and which would take a lot of time for the residents to have new shelters. Industrial buildings also not performed well because of very simple mistakes. The concrete is good, steel arrangement is good, everything is good. The only thing that workmen do on site, which is the connections, is not good. The mortar, the grout used there, and the cobbler and nut system is not good, so it ended up with such failures for many, many new industrial buildings. Non-structural systems for industrial buildings are again a kind of problem because you want to use these buildings. For example, right after the earthquake, many trucks came to the region, but no place was there to park them to remove the materials down. So many of them went back. Many of them just threw away the goods to the roads, to nearby areas. So this non-structural systems is also very critical for industrial facilities to have the continuity after the earthquake as well. And historical structures. including the first mosque built in Turkey, and many churches and many other historical buildings, structures were in the area, and many of them have been either totally collapsed or heavily damaged. This is a very delicate issue, as you know. Normally we pay a lot of attention to reconstruction or, let's say, restoration of these kind of monuments. But now there's a heavy work, very rapid work. They will be rebuilt. I hope they will be as close as the original construction. Bridges and viaducts had suffered some of them, different types of damages because of large displacements and large seismic forces, as you see here. But they were not as bad as the building type structures. I would say the infrastructure performed much, much better with respect to building type structures, again, because of better quality control. So just initial conclusions about site observations. The two large earthquakes increased the damage, and the collapsed buildings were all non-compliant buildings. None of a code standard building collapsed, though they have been damaged, which shows the inspection system during the construction and also during the life of the structure, because of corrosion and maintenance issues, were not properly done. Therefore, a huge effort is needed. Before I would say the same thing without recovery, I was saying that we have to improve the capacity of existing structures, particularly for Istanbul. Still, this is valid. And new buildings should be built better. I was saying that they are being built better, but this earthquake showed they are not, at least not everywhere in Turkey. Also, now we have another problem, how to recover in the earthquake zone. There are hundreds of thousands of buildings to be reconstructed or repaired and retrofitted. And pay attention to non-structural members and also the connections of the buildings. So this watch doesn't work, so I don't know really how much time I have, but maybe Chairman can warn me. Now it's okay. So let's talk about the situation in Istanbul. Actually, everybody knew that there would be an earthquake in this region, Kahramanmaraş. But nobody knew that it would be so strong. And again, nobody did anything, actually. Although people knew that there's a fault line is red, darkest red, and there will be some earthquake one day, and the time is almost finished because many years passed, more than several thousands of years. So everybody was knowing that there would be an earthquake at that point. And same thing is valid for Istanbul. Again, all seismologists say that the probability of a big earthquake in Istanbul, 7.5, is very huge. Something is being done in Istanbul, of course, not too much, but many steps are taken. For example, all school buildings are retrofitted or reconstructed, which is an important attempt. Hospital buildings are being renewed or reconstructed or retrofitted. So we have 1.17 million of buildings in Istanbul, of which 84% are reinforced concrete. And about 65% of these have been built before the year 2000. So this is the first priority, because obviously they are worse. Now we know that the newer ones are not perfect, but these are absolutely in bad situation. So currently we have two tools to use, which is seismic design code for evaluation of existing building. The other is the code for determination of high-risk buildings. They are brand new, quite new. But the problem is, if you apply this to these hundreds of thousands of buildings here, 631,000 buildings, you will come up with almost all of them fail, the black row. So it doesn't help to know that they are not seismic risk. We know them, actually. Maybe 5% of them are safe, but 95% of them are not safe. So we should prioritize those buildings, and we should intervene to those ones, the red ones. Probably they will cause collapses, they will cause us casualties. So the important thing is to determine which buildings are those buildings among all the insufficient buildings. Of course, if we have time, if we have money, if we have sufficient engineering service, we have to look others as well, but priority is here. So very similar to our colleague which had made our presentation, the municipality, Istanbul Metropolitan Municipality, now considers two ground motions. One is the ground motion given in Turkish seismic risk map, which is basically for design, but for assessment, again, this is used, which is more conservative. The other one is based on the different scenarios, but municipality is doing this scenario, most probable scenario, not worst case scenario. And this one is this one. So a little bit more optimistic for the other with respect to seismic risk map. So I'm not going to explain the details of this rapid assessment methodology. In some other meetings I have done that. Due to sake of time, I'm just passing to the results. As you see here, the green ones are for scenario earthquake, optimistic earthquake. This shows what's going to happen if this earthquake happens. And the dark blues are showing if the design earthquake happens. Anyway, the picture is not good. In the good case, also you can see in the table, a scenario earthquake happens. This means that this SSR means seismic safety ratio. So if it is 25, this means that your capacity is only 25% of what it should be. And this line also tells you, gives you some idea about the criticality of the building stock. As you see, more than 90% or around 80% of the building stock is not seismically safe. So if you try to solve the problem in a whole way, it's impossible. It needs a lot of money and time. So we should focus on those buildings. And that's what municipality is doing now. And basically these numbers are obtained based on individual analysis of 30,000 buildings. If you extrapolate these results to overall Istanbul, which is the study is going on, this is the general table for all Istanbul. If you look at the design earthquake, about 200,000 buildings have just capacity less than 25% of what it should be. If you look at the good scenario, optimistic scenario, this makes 100,000 buildings. And the problem is you don't know which 100 building among these 600,000. And now this is being done. When you show it on the map, again, considering two different earthquakes, scenario earthquake and design earthquake. By the way, the left side of Istanbul is Europe. The right side is Asia. You see the south-east part of Istanbul has more critical. This is town by town. So if you see a very dark color, this means that more than 50% of the buildings in this district has seismic safety ratio less than 25%. So we know which areas will be suffering more. So let's look at this chart. This chart shows the cost of retrofitting with respect to reconstruction. All points are taken from real retrofitting projects and includes architectural, electrical, mechanical, all costs. What this tells us that retrofitting of a building with respect to reconstruction is about like 40 to 20% in terms of cost. Let's say in average 25, 30%, which tells us it is rational to consider retrofitting rather than reconstruction, not only in terms of cost, but also in terms of time, because we don't have much time, and also in terms of environmental concerns. Using current buildings is much more wise. So if you look at in terms of money, for two scenarios, if you do nothing, just two lines, there are many different scenarios we studied, but this is just two studies as a summary. If we do nothing, how much it will cost to us after the earthquake? Of course, we don't spend now, it's very good, but we are going to spend after the earthquake, and these are the amounts based on which earthquake happens. And if we just intervene those buildings which has capacity less than 25% of the life safety building, then the initial cost is like that. And after the earthquake, still there will be some damages. It will cost like that. And at the end, the cost will be like that, like 1/3 or 1/4 with respect to doing nothing. So if you spend, of course, more importantly, casualties. You will avoid most of the casualties if you just touch those very weak buildings. So just some few slides about retrofitting, because in Turkey, maybe in the world, not many people believe on seismic retrofitting. Of course, if you apply retrofitting like you do the construction a poor way, it doesn't work. But if you do it properly, it works. I will show you three different ways to show that it works. One is with the actual observations made during this earthquake. In Hatay, we have retrofitted a building through actually Makedon was a partner of this project, Science for Peace project. We have retrofitted one building with Middle East Technical University colleagues. You see here Professor Uğur Ersoy, Güney Özcebe, and my young version. We have retrofitted one of these three buildings there with FRP, some FRP strengthening of infill walls and integrating it to the structural system. And the other block, when they see their neighbors are doing, they also retrofitted their buildings. But one block didn't retrofit. And then this is the appearance after the earthquake. Two survived, two retrofitted ones. The other one, unfortunately, collapsed, and about 100 people were dead in the third building, which is not retrofitted. And this is observation. Now, the next stage is experimental. I'm sorry, some of you may have seen this video before. In several years back, we have tested two identical buildings, which represent actual buildings in Turkey, typically constructed just for this purpose. This is full scale, probably the largest scale test in the world. Two buildings are tested in the same time. They are being subjected to same lateral displacements, simulating an earthquake. You see the load displacement curves below. The building on the right-hand side is retrofitted with carbon fiber polymer sheets at their first and second stories only. The black ones are these retrofitting, very light. And then the left building, you will see some slow motion records as well, collapse at 1% drift as we expected, because this represents many buildings which are not ductile. And normally, when it reaches capacity, it collapses, as expected. We are predicting that. And simply, the mechanism will be seen in coming videos in a much better way because of lack of sufficient transverse reinforcement. The column, look at this left-hand column to the top side. We are pushing now to the right side, and the column is expanding because of increasing moment. Since the confinement is not efficient, it collapses at 1% drift. And if you look at now left column, this is designed on purpose to fail in shear. Left column, there's an inclined crack, you see that. And since the stirrups are not enough again, the crack is increased and it collapsed. And you can look at again left column. That's what happens in actual buildings as well. And the other building, retrofitted, went up to 15% drift, 15% drift, which makes 45 centimeters in one story. The other building collapsed at 3 centimeters drift. This survived after 45 centimeters. These buildings are still there. The search and rescue teams use this debris. They put some mock-ups and they try to find it and so on for training purposes. And finally, so observation, experiment, and theoretical. Again, my colleague has shown some fragility curves. This shows some fragility curves for typical buildings, which is, I think, worse than your buildings. A typical building has 50% probability of collapse with the spectral acceleration of 0.15 g, very small. It can collapse at a very small earthquake. And the other curves are for different retrofitting techniques, which are all according to the code. If, for example, if you consider reinforced concrete jacketing one, the yellow-like color, you see that 50% probability of collapse corresponds to approximately 0.75 g, which means that in average, the collapse probability is reduced remarkably, or the earthquake that can cause 50% collapse is just 5 times increased. This is a significant increase. So I'm finishing with the conclusions. Obviously, the buildings before year 2000 are very critical. We have to do something. It's clear that they are not good. But this earthquake showed us the newer ones have some problematic buildings as well. Since the problem is big and sources and time is limited, we should prioritize those buildings according to highest risks, and unfortunately, we should look only at the very, very bad ones first, which doesn't mean that the others are fine. And we have to make protective measures, assessment, maintenance, repair, retrofit. We have everything in terms of codes, but this is valid for new design, which is not applied in many cases anyway. And also we have the retrofit techniques, the rules in seismic design code. What we don't have, I hope you don't leave, but after the earthquake you understand that that's missing. We don't have some code for damaged structures. To what extent damage can be repaired, what extent damaged structure can be retrofitted and brought to a new and acceptable situation. We don't have this. I think nobody has this. So, and also strengthening repairability. How can we repair? Which techniques would work well? Of course, we know something, but we are not very sure, I guess, because these are not tested very accurately. And same thing is valid for masonry. Maybe you are in better situation in terms of masonry in Macedonia, I don't know. But in masonry, we don't have any retrofit code, retrofit document officially. And more important is the last rows. Nobody knows how to do it. Even though you have some code, nobody knows how to make the quality control on site. There is no documentation. How many samples will be taken, which tests will be done, which repair material will be used when, etc., etc. Its durability, its, the temperature conditions, etc. We don't have. That's also missing. Maybe can be helpful for your studies as well. We have to do something on that. With that, I thank you, and I don't know question and answer now.
Okay, thank you very much for your interesting presentation. As far as I saw in your slides, the situation was similar like in Albania in Durrës 2019. So the similar influence factors and I have one question. So I will start with the questions. Then I will give the yes. I will give the floor also to the audience. So in which phase you are now? For example, the assessment is finished, and so now you're in the phase in the repairing. Yes,
correct.
Yeah.
The assessment is finished.
Yeah.
Very quickly. This was a. I mean, as my colleague mentioned, in Turkey, they want everything fast. They want to return normal dive fast, like the bridge construction. So there was a very big pressure on us to complete the assessment as soon as possible. So millions of buildings is assessed very quickly. Now, demolishing is not being finished because there are so many buildings to be demolished. Still, if you go any of the cities, there are many trucks going all the way, separating steel bars from concrete. And now they are using blast. Mm-hmm. Before they were using mechanical devices. Now they are just using explosive when it's appropriate. But still there is some environmental reuse issues. They are doing that, trying to do that as much as possible. So current phase is in somewhere repair, retrofit, mostly demolishing, and new projects are being designed for the city planning as well. Okay. Also for the new construction. Some already began new construction, but not everywhere, of course. Yes. It's a huge problem.
And when do you think that it will be finished? I mean, all the process. So 1 year, maybe 2 years? So.
Difficult question. Of course, I'm not sure, but I don't think in 1 year. Because already began, the ones which began will finish probably, let's say, 1.5 years. Oh. And many of them will begin much later.
Okay. Okay, thank you very much. So, other questions? Прашања от публиката? Okay. Oh.
Thank you. Professor Ilki, when was the last earthquake in this part of Turkey? And last big earthquake? And what do you think? Do we need earthquakes from time to time to remind us to design the structures as should? Or because as you see in North Macedonia, we don't have maybe earthquakes so often like in Japan, but we talk about it every year, at least on around the date of Skopje earthquake when we are commemorating. Thank you.
Actually, in Turkey, we frequently live earthquakes, once a 2 year, once a 3 year. The last one close to the area was like 2011, and in 2019 we had Elazığ earthquake. It's still a few years back. They were not, of course, as big as this one, but they have caused like casualties of 1,000 or something like that. Small with respect to this one, but still big with respect to others. But people tend to forget those things. Whatever we experienced after this earthquake is exactly the same as the earthquake we lived in 1999. Everything is same. Whatever happening is same. So we are seeing everything 25 years later. Why 99? Because 99 was a bigger earthquake. The others were not as big. This is nationwide effect. And this is also. And now again, the university's telephones were locked. Everybody said, hey, come on, look at my building, etc. And then summer came. People went to summer houses, came back. Now there's no issue like earthquake. So you are right. Some reminders would be good, but smaller scale. This was too bad. But it even doesn't work. as much as we would expect.
Прашања други?
I have one question, if
Thank you.
you have time. No, I have one question, sorry.
Sorry.
You're not finished. Thank you for your nice presentation. I have one question relating to the issue that you mentioned, and question what are your plans in a way of topic that is now, maybe also after recent earthquakes, in this one regarding the functional recovery, let's say, raised. And in that sense, for example, when we were in the field after the earthquakes in Turkey, we saw a lot of buildings from the engineering point of view standing and being, let's say, not structurally damaged, but unbelievably massive non-structural damage. And we talked with the people who live there, that were around taking their stuff and so on, and they say that they will never come back in these buildings. So, and then in this moment we noticed this psychological effect of the earthquake. So some of their relatives unfortunately died, but in some of the buildings they didn't collapse, but had heavily damage of non-structural components, which are acceptable, but for the people who live there are not acceptable. And the trauma that they survived during the earthquake, the cracks, the noise, the walls falling down, they said that they will not come back. And we heard that a lot of these kind of buildings will be also demolished, although they could be standing by the structural point of view. So what is the plan for this kind of building? Do you have any insight in that topic?
Yeah, correct. Very common problem. But legally, you can't do something else. I mean, if the building is not damaged structurally, which means that even though all the walls have been damaged, this is slightly damaged. So by law, the only thing can be done, just repair and use it. So technically, there's nothing being done. But as you suggested, some buildings, because of the sensitive things during the assessment, the guide, assessor, made it heavily damaged. Mm-hmm. Wrongly, technically wrongly, because of the pressure, because of anything. So this will be collapsed, demolished and reconstructed. But I think this is not the correct way. I'm also talking as a member of Turkish Catastrophe Insurance Pool. Because if you spend now a lot, and Turkish Catastrophe Pool is strong enough to pay all these things, because it's reinsured, most of the money will come from the other insurance companies. But then the money that Turkey has to pay to the reinsurance companies will increase, which will put us all in difficulty. So if you spend the money to incorrect building, next time you cannot repair the necessary building. So some trustable persons who the people believe, should, I think, make some explanations on the maybe media, on the television, such that if this building is like that, then you can live it in safety and so on. Because it's an unbelievably huge problem. Many cities, many buildings like 15th story, 20th story are like you mentioned. So the problem should be solved by approaching the problem in a psychological way, maybe getting some support from them.
From the technical point of view, you would say, okay, this building is okay, but the people are...
Yeah, but it's a big problem and a common problem.
Okay, thanks. Thank you for your answer. Any more questions? Okay, thanks for your time and good presentation.
Thank you very much, Professor. Can you please stay? Can you please stay?
I would like to give you this certificate of appreciation.
And also, Tina Veirum, please come.
Tina Veirum. Okay, thank you. Then we continue with the next invited speaker, Professor Svetlana Berzer, with the topic of seismic resilience of confined masonry buildings, and I will just shortly read your rich biography. Professor Dr. Svetlana Brzev has over 35 years of international academic and consulting experience related to seismic analysis, design, and retrofitting of reinforced concrete and masonry buildings. Dr. Brzev holds bachelor and master's degree in civil and structural engineering from the Department of Civil Engineering, University of Belgrade, Serbia, and PhD degree in earthquake engineering from the Department of Earthquake Engineering, University of Roorkee, India. She is currently an adjunct professor at the University of British Columbia, Vancouver, Canada, and was previously a faculty at the British Columbia Institute of Technology in Canada. Prior to her academic career in Canada, she was senior engineer at Sandwell Engineering in Vancouver and was working on projects involving seismic assessment and retrofitting of buildings and other structures in Canada, Russia, Chile, and Peru. Dr. Brzev is working as a World Bank consultant since the 1990s and is currently engaged in projects involving seismic retrofitting of schools in Central Asia. Since 2008, she chairs the Confined Masonry Network and has contributed to the development of design guidelines for seismic design of confined masonry buildings. She serves on the technical committee responsible for development of design standards for masonry buildings in Canada and is a member of the Eurocode 8 Technical Committee, 250 SC8 Working Group 1, responsible for the development of design provisions for seismic design and retrofitting of masonry buildings. She was a member of the research team that developed the Global Earthquake Model GEM. Dr. Brzev is a past vice president of the Earthquake Engineering Research Institute and is currently a director of the International Association of Earthquake Engineering. She has served as the president of Serbian Association for Earthquake Engineering since its inception in 2018. Professor Brzev has published more than 150 papers and has co-authored 3 textbooks related to design of masonry and reinforced concrete structures in Canada. In 2015, she was named a Fellow of the Engineers Canada for her contribution to the engineering profession in Canada. Thank you. We are delighted that you came, that you took your time to come from Canada to give us this presentation, and the floor is yours.
Thank you, Marco. Good afternoon, dear colleagues, ladies and gentlemen. I'm honored to be here today, and I'm grateful to the organizers who have invited me to give this talk. So I hope it's going to be interesting. I feel that the sequence of presentations is good because it, in a sense, builds on with what Professor Ilke gave the presentation, which was excellent, but it's somehow in a different flavor. So I'm going to talk about seismic resilience of confined masonry buildings, and I've divided the talk into 3 parts. One is a background, a little bit about confined masonry. The second one is planning, design, and construction recommendations for good practices, and also based on codes. And the third is numerical modeling of these buildings for case of more complex designs or needs. So first is the background, and the story has to start with Skopje. We are observing 60th anniversary of the Skopje earthquake. I am showing here a photograph of Skopje. It was a well-known Karpoš neighborhood in Skopje, where these were all unreinforced masonry buildings, apartment buildings, where many people lost their lives. And this is one of the photographs. I believe this was building number 13 that was collapsed, and other buildings collapsed. And the other reason I want to mention Skopje is that I got these photographs from late Professor Zoran Milutinovic, who I learned much about the Skopje earthquake and who was passionately studying this earthquake and its consequences. In Skopje earthquake, we'll have a few more presentations, and everybody here knows, of course, in Macedonia, 1,500 people or more died, and it has devastating consequences. Many years after, in another continent, it is Latin America or South America, and the country is Chile. In February 2010, a magnitude 8.8 earthquake took place. And the earthquake was very strong, obviously, hundreds times or more energy than Skopje earthquake. It shook or affected the territory of more than half the Chile, and it caused 520 deaths. Out of that, 100 died in tsunami, which was after the earthquake. These photos were taken in July 2010. This is a typical confined masonry building, low-rise. They have taller buildings as well, as I will show. And we visited this building, inside the building, on one of the neighboring buildings of this type. And you can see here, it's actually very interesting that people lived in a building and look at the damage. They have flowers. They invited us inside, and it was not staged. They invited us. They have full confidence in the system. This building has structural damage, but they continued to live their normal life. They were expecting this building to be repaired after some time. They were patient. So these people were trained. They live in a country that experiences earthquakes of magnitude 6 or more every 10 years. They have seen earthquakes, and they know that the confined masonry buildings in which they live are resilient enough that they will be damaged, but yes, but they will be also repaired, and they feel safe. So how do we get from Skopje to Chilean-style buildings with modern practices? So it's about a story, positive story about a system that can be resilient, and it is made of masonry, which has a bad reputation, and with a reason, even though I must say, as somebody who works in both fields, both reinforced concrete and masonry, in more recent earthquakes, I believe that concrete has a bad name. So components of confined masonry buildings, they have been used and practiced in the region. As I discussed with Darko, it's Vramena Sitaria in Macedonian. It is load-bearing masonry system, which many people mix who are not familiar, or they're from the countries where they don't have this type of system. They mix it with reinforced concrete frames with infills. But the main point is it's load-bearing masonry construction with reinforcement in the form of just a moment, no, sorry. Oops, now I want to go back. Okay, with the reinforcement in the form of vertical confining elements called tie columns, not columns, but tie column, and horizontal elements called tie beams, which are used to reinforce masonry. So this is a photograph of a building in Petrinja that was exposed to the 2020 earthquake in Petrinja, which was magnitude 6.4. It was not damaged in the earthquake, and many other buildings did not suffer any damage of this type. History of confined masonry is interesting. It was not like many other systems, of course. It was not invented by engineers. It emerged as based on a good performance in earthquakes after the 1908 Messina earthquake in Italy, which caused 70,000 deaths. That was the first situation where some buildings that were like original versions of confined masonry were found. Later on, somehow the technology was transported to Latin America, and it was found in Chile, where it has been practiced since 1930s, and Mexico since 1940s. It has been covered in the codes, and nowadays it has been since then, it has been practiced in many other parts of the world, including Europe, European countries, particularly this region, I would say, of Europe, and then Middle East, Iran, for example, then in South Asia, Indonesia, and Far East, China. So many countries use confined masonry, and of course, all practically Latin American countries. So I would just like to say, because I'll be talking about good practices and of confined masonry, what is in just few small, short description of the seismic behavior. Because confined masonry buildings are usually low to mid-rise buildings due to geometric characteristics of the structures and other factors, the behavior is usually shear dominant. And the fact is that we have these confining elements these tie columns, they serve to reinforce, to delay the damage in masonry structures and in these confined masonry structures, and to make them more stronger simply and more ductile than if they wouldn't have those reinforcement, this reinforcement that is. So these are different stages in the damage under lateral in-plane loading. Starting with the first point is diagonal cracking, then the second is extension of cracks into these tie columns, and the third is, let's say, failure or final stage. And the bottom diagram shows horizontal force versus displacement or drift diagram, which shows these different stages. So we expect that these buildings, even though the peak point is with contribution of the point 2, contribution of tie columns, very often the design codes disregard the effect of tie columns and simply consider the strength or capacity of walls based on the masonry only, which is on the safe side. On the right-hand side is a photograph of one of the many tests that have been done on the experimental studies. This is from Mexico on confined masonry. So it has been, the system technology has been researched over last 60 years in many countries, so it is well established. In multi-story buildings, this is a wall. Now, putting it in the context of a building, the typical damage that is observed in earthquakes, and it is damaged, it obviously does experience damage, and some shake table studies were done also. It is simply concentrated more on the ground floor level, but it is not due to soft story collapse or damage. It is simply capacity is, the demand at the ground floor level is highest due to seismic forces, and the capacity is more difficult to meet. So, so these are example, a few more photographs from 2010 Chile earthquake. These are typical buildings. So what is interesting, and I believe that is a limitation of the system, the technology. You cannot build 10-story building in confined masonry. Those are 4 to 5-story buildings at the maximum, apartment buildings that are in confined masonry. This is, for example, after the earthquake. You can see that people continue to live in these buildings. There could be some minor damage in these apartment buildings as well. This was nice idealistic picture. Of course, some buildings were damaged, and even 2 or 3 buildings of this type collapsed. Out of all deaths, only 10 were due to confined masonry, so this is a type of damage you can see at the ground floor. And this is another building which lost the ground floor here. This one, oops, this one here lost even the ground floor. So yeah, there was some damage, and it could have been explained, could be explained by some reasoning. In the Balkan region, confined masonry was used particularly in Yugoslavia, or in countries that are existed in the territory of Yugoslavia since 1964, when the first seismic code, so a year after the Skopje earthquake, the code was issued, and it was the first occasion when confined masonry was introduced, and subsequent code in 1981 also addressed confined masonry. Applications, as you know, in the region are usually single-family housing or some smaller low-rise, so to speak, apartment buildings, but not larger buildings of that type. These buildings were exposed in several earthquakes in the region, and most recently 2 earthquakes. One is 2019, November 2019 Albania earthquake. In Albania, confined masonry has also been practiced for some time, and this is an example of a building that lost ground floor, and it was confined masonry officially. However, they used mixed system, which is one of the things that should not be practiced at any time, with the frame at the ground floor and confined masonry walls above. So this is the reason that this building collapsed. And secondly, December 29th, 2020, Petrinja earthquake, where buildings that did not have confinement at the ground floor and have confinement at the upper floor, single-family buildings were damaged. So this is all, again, expected as according to this. So in Balkan region or in Yugoslavia, and then now in Eurocode, the Yugoslav codes and Eurocode, there were several, I'm not going to make a summary of the codes, but there were height restrictions depending on seismic zones. In the first column is seismic intensity, and then starting from the 1964 code, and then 1981, and then Eurocode, there were restrictions in height and seismic zone 5, which is intensity zone 5, which is the highest. You can see that OM is ordinary masonry or unreinforced masonry, has a height limit of, let's say, 3, whereas confined masonry in 1964 had a limit of 5 stories, whereas these limits, according to Eurocode, which has recently been introduced in the region, are much higher. So in equivalency to this, there are no seismic zones like this, but confined masonry much lower height than according to the previous Yugoslav codes. But anyways, the maximum height that is permitted for confined masonry is 4 floor levels. And this is Eurocode, and as why it's important and appropriate to talk about Eurocodes is that Eurocodes have been recently introduced in some of the countries in the region, including Macedonia and of course Serbia a few years ago, and so engineers may not be familiar with that. So where I'm going with this is just I would like to emphasize that yes, this system is resilient and performed very well in Chile and many other countries, but there are some very important aspects that we need to take care of or pay attention to in planning, design, and construction of confined masonry buildings, as I mentioned, according to Eurocode, and as well as good practices and experience from earthquakes. One of the good things, in my opinion, one of the things that makes masonry buildings more resilient to start with is the presence of rigid floors, rigid diaphragms. For masonry, this is one of the critical aspects because it improves integrity of masonry in general. So even in unreinforced masonry, it is better. Here, these photographs are from Chile, actually. So they use similar composite concrete and masonry building like we use in this region. Which is called Tralix. In their case, we call it lightweight floor slab, which is composite of concrete, steel, and masonry elements. And besides the fact that, as I said, this distribution of forces is different than the other system, which is flexible diaphragm, it is also very important for integrity. In these buildings and in buildings in this region as well, very often we have sloped roofs, which are made of timber, and these are flexible diaphragms. So in these cases, this is Chilean roof and Chilean example, and the collapse of this or damage of these buildings or the walls in these buildings is very prominent out of plane. It is for out of plane seismic loading. And this is an example from building in Chile, top floor. You can see now damage, and you can see the damage type. So this building has a ring beam or has tie beam on the top, but it was not robust enough. So what is the solution in this case? It is not to use, the solution is not to use, is to continue to use, of course, timber roofs, but to make these beams more robust, particularly in terms of the width, the horizontal dimension, and which can be estimated as a fraction of the span of the transverse wall. So there is a solution, and that is good. Very important, one of the key things with confined masonry is the location of these vertical elements. They are distributed in different ways than in, of course, reinforced concrete frames. And according to Eurocode, and I'll be mentioning what are the recommendations of Eurocode in this context, and their aim is that they have to be placed at free edges of the walls, because in order for a wall to be confined, it needs to have 2 tie columns, one at each end. Then at both sides of larger walls with larger opening, that is under B, blue, so you can see walls with openings large openings have tie columns again on the ends of the openings. C is within a wall. For longer walls, again, for the sake of out-of-plane resistance, it is very important. And then D is at intersections of the walls, of structural walls, such as shown this in the green. So all these are very important locations. This is prescribed by, prescribed, I would say, by Eurocode, but it's important to follow. I would like to emphasize the need to have confinement at the openings, because we can distribute 10 more minutes, okay, good. Thank you. I was thinking that, thank you. So we have, just a moment, I'll go back. So if you have small openings, and according to Eurocode, the area of the opening is the criteria less than 1.5 meters square, we can ignore it, so we can consider wall as confined. If you have large opening, larger than that area, then if we don't have confinement, then it is unconfined. But if you have confinement at the openings we have, we can consider this as a confined panels. And so, because then we have two panels in one wall. So instead of having just one confined panel, we have two, one on each side of opening. The other feature that is very important, and it is also a point of debate among people who are working in the field of confined masonry, is interface between the confining, the walls, masonry walls, and tie columns. And there are two ways, and according to Eurocode, again, there are two alternative ways of achieving this interface, which is believed to be critical for this joint action of masonry and concrete. One is by toothing, by extending some masonry units, as you can see on the left-hand side here. It's like a teeth. And that is why it's called toothing, and then pouring concrete to flow and to make it a good bond. It's like shear keys. And the other is without toothing, which is the situation when we have blocks, clay blocks. It's very difficult to achieve toothing. Then we can have horizontal reinforcement, which is in the form of dowels, horizontal dowels, and it needs to be there. So the question is this necessary? Experimental studies done, I don't have any evidence from earthquakes, but experimental studies done in India, a very good study by IIT Kanpur, show that it is really necessary to have toothing because it improves seismic performance. On the left-hand side is a model tested under both in-plane and out-of-plane, combined in-plane and out-of-plane loading without toothing, and the right-hand side is with toothing, so overall there is better performance, better distribution of cracking, and toothing is definitely recommended and should be used. A few very important, in my opinion at least, recommendations regarding the tie columns, design detailing. Some people, experts say in publications, yeah, this is a system, you can do anything with it and it's going to work, again, it's not going to be damaged. That is not true. It depends. Tie columns are very important. Their reinforcement, both longitudinal, vertical bars, and transverse ties are very important. For longitudinal reinforcement, it could be determined in prescriptive manner for small buildings, but for larger buildings, it has to be determined from rational calculation procedures, similar to what we do for, let's say, reinforced concrete walls, reinforced masonry walls, where we have to consider both tension and compression steel in these tie columns. I'll show here. So we consider these tie columns that they have both, we can design that based on for combination of axial load and bending using interaction diagrams or any other way. For transverse reinforcement, Eurocode prescribes minimum 5 millimeter ties at 15 centimeter spacing, not more than that. Some other codes prescribe, Eurocode doesn't, and we had some debate, it's not going to be there either. It prescribes smaller spacing at the tops and bottoms of the columns of ties at, let's say, 100 millimeter, 10 centimeter spacing, and it is a good practice. We have seen in Chile that these locations are indeed critical, tops and bottoms of the columns, and you can see here how the columns, tie columns were damaged because of inadequately wide tie spacing. So that matters. Of course, it didn't collapse, but it is severe damage. Finally, last but not least, it's very important, quality of masonry is really critical. We cannot put garbage in the wall and expect this to perform. Minimum strength requirements have to be followed. There are lots of debates in the region and pressures from industry to reduce the strength of the masonry. It is very dangerous because it is load-bearing masonry construction. It's going to be as good as masonry is good. Many studies have shown, I've been a co-author of a paper with colleagues from many countries, with Perez Gavilan, first author, which shows clearly that shear strength of masonry is proportional to compressive strength. So the compressive strength of masonry is directly proportional to strength of masonry units. So if you have a poor quality of units, everything is going to be inadequate. So finally, the last topic is numerical modeling. Eurocode permits two different approaches for analysis. One is for simple buildings, which are regular, low-rise. There is no need to really do analysis, modeling and analysis. There are simple rules, which I covered in the paper, but I don't have time to talk about now, which are based on the percentage of walls in one direction and the other direction, so-called wall density, wall index, and that is it. And if the building is irregular or taller, it is required to do engineering analysis and design. Design is covered by Eurocode 6, and analysis approaches are covered by Eurocode 8. However, Eurocode 8 does not give numerical modeling approaches, and it is a bit tricky. It's trickier than some other systems, like concrete frames, certainly, because of the nature, as I said, composite nature of masonry. And there are few modeling approaches that can be used. I mentioned in the paper as well, Strat and Tie model, which is macro modeling approach, and equivalent frame model. These are macro models, and then finite element model, which is micro model. Macro modeling approaches are more practical for real design applications. I personally like Strat and Tie model, which is integrated analysis design approach, and it simulates a building like a truss, like you can see here, a simple panel. You have tension elements, which are called ties, and compression elements, which are called struts. As you can see, they're joined in the nodes. And the key point of Strat and Tie model is that we can assume, for example, yielding in the vertical, in this longitudinal steel in tie columns, and you can find the capacity of the structure. That is the way to use it. It is often misinterpreted and made equal to equivalent Strat model, but it is not the same. And it requires thinking, it requires, which is very good, it's not just using computers, because it requires development, understanding of what is the direction of struts and ties in certain direction of forces. The model, lastly, and these are my last few slides, I personally am in favor of equivalent frame model, which has been used for modeling of reinforced concrete shear walls for many years, since 1970s. And it has been used for confined masonry very effectively. And the concept of this is that this is an example of an actual wall with its confining tie columns, and equivalent frame model is simulating this as a transformed section with the vertical, with the wall modeled as a vertical element, and then horizontal elements are representing the effect of slabs. So here are some recommendations from Mexico. They have been using extensively this model, and they have horizontal elements have their two types. One is a rigid beam, which is here, which is modeling the part of the wall that is next to that is a part within the wall width. And then the other part, which is a slab, and there are different recommendations how to take it. This is needed only for 2D models. For 3D model, there is no need for having effective depth. This is an example of a typical actual, again, wall with openings, and on the right-hand side is a Strat and Tie model. So you can see here also that with this, there are some complexities, further complexities within this. And I have shown here modeling of parapets, which can be also additionally rigid sections. So it is a very good model. It's a modeling approach. It's practical. However, it is difficult to do, time-consuming for using a general-purpose software packages. And for that reason, I would like to mention that there is a software which I recently got to know and started to use, which has been developed and has custom built features for numerical modeling of specifically confined masonry, and works. It's IamQuake software and can be used to do both linear and nonlinear analysis, and it has good input features. So I'll just show you an example of different modeling approaches. Usually it is equivalent frame based, And then these are examples which exist there. We are now working on another case study example from this. So it assumes rigid diaphragm model for the building, which is suitable for confined masonry. It can also model reinforced masonry and non-reinforced masonry. And you can get results, internal forces, displacements for static analysis, as well as pushover. It can be done if it is needed, but for practical purposes, we usually need static analysis. So in conclusion, I didn't try the conclusion slide. Confined masonry can be made resilient. It is resilient, and it can be resilient provided that it is performed correctly. There is a lot of belief that it is just a prescriptive system. It could be prescriptive, but there is a potential for using it for a bit taller buildings than what it is used, with using engineering analysis and with more education and more, I would say, promotion. It could be a very good alternative to frame, and maybe better to frame systems for this category of low to mid-rise buildings. I would like to help again organizers, Wienerberger, who sponsored my travel expenses, and Nemanja Krtinić, PhD student from University of Ljubljana, with whom I'm working currently with on the applications of this Quake software. So that is all. Thank you very much. And sorry if I've gone over time.
Thank you for a good overview and nice details in your presentation. And we ask the audience for questions. If the audience is shy, I will start with the first one, if it's okay. So you mentioned in your presentation a couple of interesting aspects, and maybe can you give a comment about the size of the tie columns in the case of, let's say, modern confined masonry, or we today know that due to the energy efficiency demands, we have now the blocks of 30, 35, even more centimeter of thickness. And what do you think, or what's your opinion about the size of the tie columns? Because usually they are 20 centimeter, 20 by 20 more or less. So should they follow the thickness of the wall or stay in smaller size? How that can have results in the behavior of the confined masonry walls?
Thank you. It's a very good question. And in fact, when I looked at the systems in Latin America, they often have just 15 to 20 centimeter thick walls, so they don't have the same thermal regulations as here in Europe. Here I know that there are 25 centimeters. I feel that not sufficient studies have been done, but I believe that the key aspect is the relative stiffness of these tie columns relative to the wall. And the issue in these thicker buildings with the tie columns which match the wall thickness, let's say, end up being 25 centimeter or so in order to match the wall thickness, is with the smaller walls, shorter wall lengths. And that's where it's a question of how does it behave, because if the tie column is so thick, so maybe there should be some solutions for making the thickness can be the same, but more narrow, so it can have rectangular section, if you understand what I'm saying. Mm-hmm. But for the longer walls, you should still have the case. So maybe there should be some guideline about the width of the tie column in case of relative to the wall length, which could be, it can be numerically estimated, and there are very few experimental studies on that. There is only one that I know of in Peru, but it definitely, relative stiffness is the key there.
Okay, so definitely work to be done, huh? Thanks. More questions? Okay, then just one final small question. Sorry, maybe I'm boring, but it's interesting if I can. You mentioned in one slide the minimum strength of units. But it was written like 5 megapascal, right, for modular clay blocks. Mm-hmm. What do you think about the use of the other types of the units from different materials that we know from the practice, and what should be their compressive strength, or should be follow the same levels, or what's your opinion?
Yeah, I believe that this 5 megapascals is absolutely the minimum value. If we were to use, let's say, concrete blocks, at least I can say for Canada, for load-bearing masonry, it's 10 megapascals is the minimum strength, so it would be different. And for bricks, it could be also higher than for the modular unit. So the question is then, do we result in different strength of masonry? I think it's simply the minimum characteristics of the units or masonry elements that we use that we have to go by. So in Mexico, they use all these kinds of units in the same country, and they have different limits, minimum values for different units. So you wouldn't have the same strength. So, but in Europe, as I understand, and based on discussions with the Europe Code 8 group, everything is just focused on these clay modular blocks because they're practically the only type of elements that is being used. But in other countries and other continents, there is a variety of units in the same, of elements in the same country.
Okay,
Yeah.
thanks.
Yeah.
Okay, thank you.
Продолжуваме понатаму со спонзорите. Сега на ред е Platinum спонзор Радинг.
Можеш напред, можеш напред. Добар ден на сите. Јас сум Никола Узунов, градежен инженер, работам во компанијата Адинг од Скопје. Денешната наша презентација, компанијата Адинг ќе биде во духот на овој симпозиум и во духот на одбележувањето на 60 годишнината од земјотресот во Скопје. И презентацијата е со тема квалитетниот бетон како гаранција за сигурноста и трајноста на армирано-бетонските конструкции. 60 години после земјотресот во Скопје. Градот е изграден, поголем и може би поубав од оној кој го паметат по старите генерации, иако они никогаш не би се сложиле нели со тоа. А тоа што ни останува на нас денеска е покрај тоа да го одбележиме оваа годишнина е и да се сетиме на пораките, односно на лекциите кои ни се пренесени од овој настан. Првата работа што би ја напоменал е дека солидарноста на луѓето во светот нема граници. Илустрација за тоа е Скопје, кое е повторно изградено, делумно и благодарение на помошта која дошла од целиот свет, токму во периодот кога била најпотребна. И повторно символ на тоа е и ова слика која ја има во позадината на слайдот, која авторот Пабло Пикасо ја подарил на Музеот на современа уметност на градот Скопје после земјотресот. Втората лекција се однесува повеќе на нашата фела и не подсетува на тоа колкаво е значењето на квалитетот и сигурноста на конструкциите кои денеска се градат. Нормално, тоа веднаш ни го поставува прашањето дали денешните конструкции имаат доволен квалитет за да ја гарантираат сигурноста на корисниците, на граѓаните. Секако ова е комплексно прашање, не може да се генерализира, али една од аспектите што можеме да кажеме дека одат во прилог на таа сигурност, генерално на конструкциите, е дека квалитетот на бетонот денешен служи како гаранција за сигурноста и трајноста армирано-бетонските конструкции. Што значи квалитетен бетон, кој ќе кажеме? Тоа е бетон пред се кој ги има потребните перформанси да може да биде правилно вграден со онаа технологија која ни стои на располагање. Во тврдната состојба бетонот мора да ги има сите оние перформанси и јакостни карактеристики, но и други, отпорност на дворешни влијанија и така натаму, со кои ќе се сретне, односно на кои ќе биде изложена конструкцијата во текот на целокупниот период на експлоатација. Тоа се атмосферските влијанија, дејство на мраз, соли, на карбонизација, особено во урбаните средини и кај инфраструктурните проекти, како и други влијанија кои произлегуваат од намената на објектот. И овие перформанси конструкцијата мора да ги задржи во целокупниот период на експлоатација. Дали тоа ќе бидат 10, 50 или 100 години, значи не сме да после некое време да се толерира дека опаднал квалитетот на бетонот и на конструкцијата, мора да биде, перформансите мора да се задржат во целиот период на експлоатација. Што е тоа што ни помага на некој начин за да ги постигнеме сите овие барања? Тоа се стандардите и кодовите кои ни помагаат да ги одредиме и да ги постигнеме тие перформанси. Кога станува збор за бетонот, тоа е европскиот код EN 206, кој покрај тоа што ги дефинира карактеристиките на бетонот во свежа и тврдната состојба, се фокусира на трајноста на бетонот. И дури има цел спектар дефиниран цел спектар на класи на изложеност на бетонот и дава препораки за состав на бетонот во зависност од соодветната класа на изложеност. Ова само за илустрација ги покажувам, овие се главните групи на класи на изложеност. Флаерот овој истиот флаер кој го покажувам го има и на штандот на Адинг. Ако некој е заинтересиран може да земе. Останува уште, кога зборуваме за бетонот, да кажеме и за барањата кои се специфични за новото време, за 21. век, а тоа е дека бетонските конструкции мора да бидат одржливи, мора да внимаваме на количината на емисиите на CO2 во атмосферата. За жал, производството на индустријата за производство на цемент е еден од поголемите емитери на стакленички гасови глобално и се прават сите напори, исто така глобално, значи да се намалат тие емисии на CO2 пред се со користење на замена за клинкерот во цементите. И друга работа е оптимизација, што треба да внимаваме, тоа оптимизацијата на средствата како за извадба, така и за одржување на конструкциите. Наједноставно кажано, тоа значи ајде да градиме поквалитетни конструкции и истите да ги одржуваме, наместо да плаќаме периодично скапи санациони работи. Да споменам и збор 2 за компанијата Адинг, она е основана неколку години после земјотресот во Скопје, 55 година. 55 години ќе биде нашиот јубилеј следната година. Името на компанијата Адин е акроним од зборовите адитиви и инженеринг, што самото укажува дека уште од своето основање фокус на компанијата е развојот и примената на адитиви за бетон, но исто така и промоција на примената на современи технологии на бетон и за примената на специјални типови на бетон со високи перформанси. Во годините после или децениите после земјотресот можеме да кажеме за Скопје дека е доминантно армирано бетонски град, односно конструкциите, меѓу кои има многу врвни дела со трајна вредност, се градени во Скопје и мислам дека тој тренд во известна смисла и денеска е задржан, дека најголем број од објектите секако се предоминантно се армирано бетонски конструкции, а исто така смислам дека и трендот на примена на некоја современа технологија на бетон за изведба на убави и репрезентативни објекти исто така е задржан, што е комплимент за сите луѓе од фелата и за изведувачите нели во Македонија кои се одважуваат да ги применат овие технологии. Ова се само за илустрација покажувам некои фотографии кои се одбрани од градот Скопје, нели да бидат, некои се постари, некои се понови, генерално ги препознаваме сите. За жал Скопје не е само на мапата на сеизмички активните подрачја, се наоѓа високо и на мапата на загадените, на средините со високо аерозагадување, што покрај тоа што делува негативно на здравјето на луѓето, делува негативно и на перформансите на бетонот, односно на армирано-бетонските конструкции, пред се поради појавата на карбонизација. Се извинувам. Што можеме да направиме за да го превенираме овој ефект? Нормално новите објекти да ги изведуваме со перформанси соодветни да може да ги примат овие негативни влијанија, но веќе постоечките објекти потребно и пожелно е да се штитат. АДИНК исто така во својата програма има бројни материјали и системи за заштита на армирано-бетонските конструкции, или доколку истите се наоѓаат во некоја фаза на позначајно оштетување, значи потребно е нормално прво да се санираат, па потоа да се заштитат. Ова е повторно некои референтни објекти во Скопје кои се каде се применети овие материјали за санација и за заштита на армирано-бетонските конструкции. Ова е последниот слайд, само за ете како заклучок некој. Денешните армирано-бетонски конструкции се бара да имаат 100% сигурност и функционалност во целокупниот период на експлоатација. За тоа да се постигне, истите треба да се проектираат и да се изведат со примена на сите препораки и сите прописи за асеизмичко градење. Самиот бетон треба да биде со својства соодветни на барањето од проектот, но и на степенот на изложеност на во кој објектот се наоѓа. За таа цел ќе ни помогне европскиот стандард EN 206. И поради големата агресивност на средината, веќе изведените објекти, потребно е да се штитат, да се мониторираат, да се направат можеби помали некои интервенции на време, за да се спречи, односно да не дојде до потреба да се прават големи санации. И благодарам.
Благодарим.
So next, platinum sponsor Bechtel and Enka.
Okay, no problem, it's okay. Hi everyone, I am Serkan Ülker, engineering manager of Bechtel Enka joint venture in North Macedonia. Today we want to shortly present you the corridor construction and Bechtel Enka's experience in Balkans. Within over 30 years of operational history, Bechtel Enka developed its own core processes, method statements, and these are the reflection of our know-how and lesson learned. And those procedures and processes are the basis of our safe and successful completion of the projects in time. So I want to present you the key challenges that we face during construction. The first item is the implementation of the environmental health and safety culture. Whenever we start the works, first we need to give this all the orientation and the trainings to the new employees. Later on, during the work process, we have start cards and toolbox talks, and for each construction activity, we have the risk assessments and safety walkdowns, and to keep everything safe and in an environmental manner. So up to now, we have over 8 million man-hours without any lost time accident, and our target is 0 accident. So another key challenge is the implementation of the quality culture. Quality is one of the major items that we should follow. Our target is zero rework, and we are trying to give all the trainings to our direct hires and also our subcontractors. So the work should be completed in a quality way. And we have the quality management systems and audits, and also we have the quality awards to push as much as these sections. So another key challenge is the people. So once we have, our projects are mainly international projects. We have many workers, many engineers from different multicultures and ethnic groups. So we are working as a team with these international members. And we are supporting the social activities, we are supporting the educations, we have good communication with the faculties, also even in faculty in North Macedonia. And also we are working with the local stakeholders and local community. We are going and visiting them and asking them how we can help to them. And these are the technical challenges that during construction, we have always the topographical, geotechnical, and climatic difficulties. As you are aware that the work is not done always on the summer and during day. We have many challenges, especially in topographical sections. So another challenge is expropriation, where most of the cases we have the problems with the expropriation, and there are another items that are ecology and utilities. So during construction, we have to complete the access roads, and from where we will get the material. We are looking for the borrow pit and quarries, how we will transport the materials, and where the people will live during construction. So these are the key items, and another important item is the schedule and how these works will be managed. For us, the schedule is the execution of the project in planned duration and inside budget without compromising any environmental safety and healthy and quality issues. And of course, the client satisfaction is the most critical item. We are preparing our detailed schedules, major items, milestones are studied. So over 30 years, we completed 6 motorway projects in the region, and 2 are ongoing. And during these projects, we have over 90 kilometers of motorways completed, and over 48 kilometers of bridge, 350 million metric cube excavation, and 5.7 million metric cube concrete was poured. So these are the projects that completed. The first one was from Bektelenka joint venture, was Ankara-Gerede motorway project. It was 230 kilometer motorway in Turkey and completed in 1999. So another one was in Croatia, this corridor 5B and Route 1, Bregana-Zagreb-Dubrovnik motorway. It was 156 kilometer and completed in 2004. So these are the pictures from Croatia. And another motorway was in Romania, Autostrada Transilvania. The road was 415 kilometers in total, and Bektelenka completed 115 kilometer section in Romania. These are the structure types that we have, launchers. And we have this Reșan-Kalamash motorway, Albania. Most of the people already visited this section. It is 61 kilometers, and it was completed in 4 years in 2010. This is the tunnel, that 5.5 kilometer tunnel we built in Albania. And this was the tough terrain, difficult terrain conditions. Another one was completed project in Kosovo, Route 7, and this project was completed in 2013, 78 kilometer motorway, and the first 38 kilometer was completed in 18 months. This was a fast track project. These are the photos from Kosovo. And the second was also in Kosovo. This is Pristina-Hanezit motorway section. It was 65 kilometer. And in that section, last 15 kilometer was really difficult. We managed to build this 5.7 kilometer bridge. Most of you most probably visited that when you drive to Pristina, and this road was finished in 2019. This is interchange in Pristina, and some side photos from construction. And another ongoing project we have in Serbia now, it is Morava Corridor project. It is 112 kilometer motorway. It is in the Morava River Valley, and the scope is construction of motorway, and more than 30 kilometer river regulation of Morava River is included. So the first section from Pojata to Kurusha was opened, and the construction is ongoing. And these are photos from the Morava Corridor project. And now we started in North Macedonia, Corridor 8 and Corridor 10D motorway projects. Corridor 8 is Tetovo-Gostivar, Gostivar-Bukačine, and Trebenište to Struga, Kelfasan section. And Corridor 10D is Prilep to Bitola. So this is 109 kilometer dual carriageway. And significant features are that we will work we are already working in North Macedonia in 3 different geographical locations. It is seen in the map. And we will utilize the fast-track construction methodologies, and local labor and supply chain engagement is the main key in our project. So key quantities for this project in North Macedonia, 109 kilometers of the motorway we will build, bridges are 34, and overpasses are 34. We expect nearly 21 million meter cube excavation, and concrete will be 620,000 meter cube. So during construction, we got also awards from international institutes, and we will keep looking for new awards from our ongoing projects. So thank you very much for your time.
Thank you.
Наредниот спонзор е Golden Art.
Golden Art.
Има представник од Golden Art? Нема? Добро. Аха, добро. Видео. Ќе оди видео. Па наредно...
Small technical problems.
Сега отидем там, где сменам и ти ги опустиш, разбираш?
Само навлево и после да опустиш.
Thank you. The last for this session, platinum sponsor Penetron and Isotechna.
Just a moment. It's gonna break. I will. I can give you also this. Yes. Thank you. It's okay. And again, sorry, can I pass here?
You can just pass here for next page, this for back page.
Okay, thank you. So, hello, I'm Theodore. I'm Managing Director of Penetron Greece, responsible for Europe Southeast. So, we're talking about business, but I would like also to be helpful with this symposium. So, we're going to talk about durability and technologies and how we can help with our crystalline technologies to push technologies a little bit further. So, integral crystalline technologies for durable and sustainable concrete structures. So, this is a very nice photo from a ship built in 1943 with crystalline technologies in order to provide waterproofing. So I think we all agree that crystalline technologies can provide waterproofing, at least. So the Germans, during the Second World War, were testing these technologies in order to build up big ships. That time Hitler wanted to invent to England with big ships from concrete. So these technologies, after the Second World War, developed in United States and Canada because of most of the scientists went there after the war. And concrete crystal growth technologies already well known from the 50s, mainly used in infrastructure projects for big dams, for industrial projects, and later also for residential. Around 70s, Penetron company developed its own crystalline technology and developing a lot of products, starting with cementitious slurries that were penetrating inside concrete. Just to make it more interesting for you, today we have technologies that the crystalline formation can penetrate more than 1 meter inside the concrete and develops crystals up to 0.5 millimeters. So we can heal, by self-healing, cracks up to 0.5. So our Penetron is distributed in all these countries in Southeast Europe, just to see our organization. And since we are going to talk about concrete, we have to understand about the concrete pathology. And of course, concrete is what the architects love very much. Why? Because you can have all these structures from concrete, easy to design it, not expensive, to be honest. And by the way, for those that you don't know, it is the second most consumed product on Earth after water. That was a nice story. But unfortunately, we have a lot of problems. We discuss about earthquakes, we discuss about problems for corrosion. And what is, by the way, the quality status in all over the world? I have some statistics here. In the USA, 54,000 out of 613,000 bridges were considered as structurally sufficient, very small percentage. In Europe, around 46,000 bridges in 14 countries, and 30 of the bridges usually was corrosed, from the reinforcement, of course. In Greece, we have around 3,000 bridges over 6 meters that are having problem, and we had 78% that reaching its service life cycle. Of course, we had problems from corrosion in Miami, if you remember. Also, that bridge in Italy, a lot of people died there, of course. So sometimes the story is not so nice, and we have to do something about that. The problem is, of course, the durability of the concrete and the structures. And I had the durability from the Concrete Institute, for the American Concrete Institute. So durability of hydraulic cement concrete is defined as its ability to resist weathering, action, chemical attack, abrasion, or any other process of deterioration, and durable concrete with retain its original form, quality, and serviceability when exposed to its environment. With simple words, durable concrete should stay still, okay, through the years. Apart from this, we have all the global trends. You see, this model was before 14 years, but we found out how modern it was at that time. It says that the global trends for sustainability and smart use of resources needs to have durable structures. The second, new financing models, ROI, return on investment, demands the same. Demand for long service life, this is easy to understand. And look about the last one, supply shortages and increased cost of materials. The last 2 years, we all suffering about increased prices, about lack of raw materials. And this is the main reason that durability of concrete and structure, of course, is very, very important for all of us. So let's see the main factors affecting concrete structures. Of course, corrosion, alkali-silica reaction, freeze-thaw and sealing damage, carbonation damage, aggressive chemicals, and groundwater damage. This is 80%, 82%, by the way, of the main problems. The rest are dynamic, like the seismic problems, but also, if you go back also with the reports from Turkey, we saw that a lot of problems was human designing or corrosion. So almost 92% is final the problem of all these factors. So if we can solve the problem that all these factors are creating, then of course we can provide durability. This is how we are thinking. Okay, corrosion, easy to understand. Penetration of the water, that is a vehicle of all the aggressive materials. And the target is the rebars for the corrosion, of course. But I think one photo is more than 1,000 words. So finally, it expands. I mean, the rebar expands. And finally, the reinforced concrete is not reinforced anymore. And a nice photo from a bridge in Greece can solve this problem because of the corrosion. There was one fisherman that was seeing that photo for many years with his boat as he was finishing. Of course, you don't have to be an engineer to understand that this bridge will collapse, of course. Okay. So, other problem of alkali-silica reaction, well known as cancer of concrete. We know, of course, that the water penetrates and humidity through the microcracks and provides humidity to the aggregates, and some chemicals of the aggregates start making a kind of a gel, and this starts exploding inside with the water. And this is how it works. So it is like an internal bomb in the concrete. And of course, due to this hydraulic pressure, we have a lot of cracks. And this leads to, of course, a big problem for the concrete structures. This is how it looks in the microscope. But of course, you can see how it looks in the real projects. Sometimes it looks like a freeze-thaw problem, but it is completely vice versa, because in the problem of the freeze-thaw, which is the next problem, by the way, the water penetrates, and we have the problem when it turns to ice from the layer to inside. And sometimes, of course, we have double problem when we use some salts in order to protect from the ice. By the way, we have a nice wall from Kosovo, if I remember, where we have double problem of freeze-thaw and dissolved ice that they use there. So this is chemical problem and freeze thaw as well. Carbonation damage, again, the water and humidity is the vehicle that the CO2 is penetrating inside the concrete. The main problem is that we have decrease of the pH, and when the pH drops, the next problem will be corrosion, of course. Again, the humidity in the water, of course, here creates the problem and the mechanism. And we see how it looks. Of course, we have also methods like phenolphthalein to measure the carbonation damage, of course. Another problem, aggressive chemicals and groundwater damage. Again, the water with many difficult mechanisms is penetrating. You can see a photo at the right from a bridge in Axios Bridge, Bardar River, by the way. Okay, so you see that this problem happened because of the waters coming in, because of the de-icing salts, and the de-icing salts created all this problem because the drainage pipes were not working sufficiently. So easy. You can see also one wastewater tank from Cyprus, and this problem happens just after 7 years. Okay, so you understand that the chemicals are creating a lot of big damages, and the mechanism is very easy. The water carries all these chemicals inside concrete and creates damages on the surfaces, new cracks and penetration through that. This is a wastewater tank just after 7 years. You see how the problem started when we don't have a good protection. So, what do all of these damaging factors have in common? If you remember from the high school, water. So the water is the vehicle that transfers all this aggressive material inside, and we see either corrosion or carbonation, all the other problems we said. And why? Because concrete is a permeable material. So let's think now like our ancient Socrates in Greece. He was saying that, okay, we found which is the root of the bad, then we can make a solution. So if the problem is the concrete permeability and the water penetrates, if we reduce the concrete water permeability, of course then we are reducing the problem which was corrosion and all these other problems. So then we have to agree that the water is the common of the damaging factors for concrete deterioration, and the reduction of permeability is increase of durability. So if the water is the main enemy, we have to decrease the passage through the concrete pores and cracks. And of course, as we said, reduction of permeability is equal to increase of durability, but what we need is durable structures. So the main problem was that we have a big gap between the designing lifespan and the real lifespan of buildings and structures. And we use this technology in order to decrease the problem. And according to these researches we made before 15 years, we can provide 60 more years protection to the concrete in comparison with the orange bar, by the way, is the normal sample of C3037 in a very aggressive environment. And with this technology, we provide about 60 more years in an aggressive environment. So these technologies of crystalline products are based in, I would say, in the green technology. The most aggressive material is cement. It's a cement-based product. And I will show you a small time-lapse video to understand how this system works. As an admixer, when the water is passing, we have sound. Don't hear everything. So you will see the time when the water is passing, the production of crystalline formation is coming. We are just a little bit more than 60 hours now. So you see that the water is stopping. The crystalline formation is very visible. Of course, the water is stopped. This is 4 bars negative pressure. And you can easily understand how this technology works before and after. So I will pass this video. So the crystalline formation is the result of these technologies. You can see also, even in a slurry form, penetrates inside, so you can see cores of 35 centimeters just after 2 months. And you can find a full range of crystalline products that can be admixtures, can be slurries, can be repairing systems, even dry shake hardeners. For the admixtures, we have developed a green tracer technology. So with this green, nice color, you can see that the system is working. The mixing is at the right ratio of 0.8% of the cement weight, and everything is going fine. You can see on the bleeding water. So, as we said, this crystalline technology has slurries, mortars, also ejection system, all with the same technology, and of course, fast-setting mortars as well. So you can provide protection, permanent protection of concrete, either in a new structure or existing structures. And of course, for cold joints, we are using either water-expanding strips or PVC membranes for cold joints or moving joints as well. Regarding testing, we are running thousands of tests in more than 100 countries all over the world. These are the tests we made for the International Cup in Brazil and also for the Olympic Games there. So just to understand how the system is working, these are tests according to the American standards under 7 bars of negative pressure with a crystalline admixture. You can see that in the first week, the water passes inside, no difference with the white sample. But what happens the second week, 7 bars pressure again, you see that there is a decrease due to the crystalline formation, and this continues the second and the third week. So after 4 weeks, we have a 0 water penetration. It works like a coating from the beginning. Okay, close to magic, but this is how it works. And you can see also in the samples. And in the microscope, you can see that after 3 to 4 weeks, the crystalline formation is full. And this is, by the way, a self-healing effect, which means again and again, we have the new production of crystalline if new cracks happen and the water is passing. We have tested with IMM Institute in Switzerland, so we can understand how it works and how deep it can go, and also about the width of the cracks that can be up to 0.5 millimeters guarantee. Tested also according to EN 206. We have tested all different categories of concrete, and the results are more or less the same. So you can see for water permeability, the green bars are the samples, and the blue, of course, you cannot see the blue because the blue is close to 0. Okay, so this means that we have waterproof concrete and, as we said, total concrete protection. And the same stands with very good results in the decrease of carbonation. This is, by the way, with the University of North Greece, of Thrace University, after 900 days. 900 days, this means a very long, okay.
Time.
Yeah, okay, I'm running fast. Okay, so I will pass this testing. Just show you some nice projects. This is good, just to understand. So, through the crystalline waterproofing, we can provide, as we said, durability, and through durability, we can have sustainable structures. And about some nice projects. I'm running very fast. You can see wastewater treatment plants, also by shotcrete, can be applied. Something stopped here. Okay, in very big hotels. So you can understand by this photo how the system is working. So it's concrete and crystalline formation that protects totally the concrete. Also for shotcrete, as we said, deep basements. Also for bridges and bridge repairs, power plants. You can understand how difficult it is to resist in such water with salts. University of Cyprus, and just to go a bit here to show you how it works in these 3 weeks. So this is just first week after filling this big tank of 10 meters. Maybe somebody understands that the system needs some time to work. And this is just after 10 days. And if you go closer, you can see also the crystalline formation. Okay, so thank you very much for your patience. Okay, you can pass. So for questions, you can pass from our stand so we can discuss everything there. Thank you very much.
Thank you. Yeah, coffee is ready, so thank you for being part of this session.
10 minuti pauză. 10 minutes. Haide.